Okay, let's unpack this. We are diving into a realm where the shiny promise of AI meets the gritty reality of network defense.
It's a huge topic right now.
It is. Imagine this. Your security dashboard is glowing green, everything looks fine, your firewall seems solid, but underneath it all, one of your core network devices is actually wide open, and the AI scanner, it missed it completely.
That scenario you just laid out, that's the core of the one-click mentality we're seeing. People treat these AI agents like they're infallible auditors.
Right, run the scan, see the report, job done.
Exactly. It's comforting, sure, but as our sources show, relying solely on that automation is a massive, massive liability, especially, when you hit that Cisco Layer 3 boundary.
Exactly. So our mission for this deep dive is really to prove out that quote from the source material. AI can see a packet, but it rarely understands the data.
It's a great quote.
We're exploring that critical difference between using automation just to speed up tasks versus relying on human architectural knowledge to create real strategic resilience.
The central conflict here is that automation is built for speed, for pattern recognition. But human judgment, that's what's necessary to interpret context, to identify deliberate network deception, and, well, to address that huge AI blind spot that exists in pretty much every automated system out there today.
And the most immediate, maybe the most dangerous trap these AI scanners fall into involves the most basic thing on a network report: the filtered port status.
That's where the deception begins. So when an AI scanner does its thing, its reconnaissance, it attempts a standard TCP three-way handshake. It sends out that initial SYN packet to a port.
Okay.
And if the AI doesn't get a response back, no SYN ACK, no RST packet, the dashboard just automatically labels that port filtered.
And I imagine most analysts, especially junior ones, they see filtered and think, great, the firewall's working.
That is the number one assumption. They see it as a confirmation of success. Firewall did its job, port is blocked, perimeter safe, they move on. It's the easiest thing to think.
And that assumption is precisely what gets exploited.
It is. What's fascinating here is the architect's reality. The AI is making a decision based on a lack of data. The absence of a response does not guarantee success.
Doesn't mean it's blocked.
Not at all. That lack of response could be 100 different things.
So give us the top culprits, the things an AI scanner will never ever consider when it confidently reports filtered.
Okay, the three big ones are a misconfigured Cisco access control list that's just silently dropping the packet,
Right.
an aggressive ICMP rate limit that's intentionally slowing down or suppressing responses, or, and this is the worst one, a deliberate silent drop policy on a layer 3 switch to hide the device's presence.
So the AI reports security because it couldn't get a response, but the device is actually alive and kicking. It's just ignoring the scanner.
Precisely. The network might look secure on that automated report, but it's actually fully functional, maybe with a vulnerability exposed, and the AI just got tricked by an intermediate appliance.
It's the difference between a secure environment and one that is just quiet.
Exactly. And if you blindly accept that filtered report, you are introducing noise, or worse, a huge false sense of security into your entire analysis.
So how does the human analyst cut through that noise? If the AI is being fooled, what's the simple manual check that confirms a host is alive no matter what the firewall is doing?
This is where that human advantage becomes so critical, and it really relies on knowing your IP protocol headers. The analyst has to manually verify the host's status using the simple ping command.
Just a ping.
Just a ping, but specifically you have to look at the time to live flag, the TTL.
The TTL. Okay, that's the crucial detail. For you listening, what is the TTL doing and what are we looking for to expose this deception?
The TTL is basically a counter. It's a hop limit that stops packets from looping around the internet forever.
Yeah.
Every time a packet hits a router, that number goes down by 1.
Okay.
When you manually run that ping, you're looking at the TTL value that comes back. If that return value is either 64 or 128, you know the host is alive, period, regardless of what the port scanner said.
Why those two specific numbers, 64 and 128?
They're the standard default starting points for the two major OS families. If you see a 64 coming back, you are almost certainly talking to a Linux or Unix-based system, which is very often a Cisco device.
And 128.
That's Windows. If you see 128, you're talking to a Windows host. So even if the firewall is dropping your SYN packet and tricking the AI, that simple ICMP ping proves the host is active and responding. The intermediate device is just creating noise.
Wow. I can just imagine the frustration. The AI says you're secure, the analyst runs one command, sees a TTL of 128, and boom, suddenly you realize you're not celebrating a firewall success, you're investigating a misconfigured network device.
It shifts your focus immediately. You go from thinking a port is closed to figuring out which router or layer 3 switch is configured to silently drop packets.
Which leads us right into the next stage. Once we've used that TTL check to see through the deception, the analyst's workflow has to move to achieving 0 false positives.
Right. You have to move past the basic scan results to verifying the fundamental validity of the data itself.
So before you even investigate a vulnerability the AI did find, you have to make sure the scan itself wasn't just broken.
Exactly. You have to validate that the scan wasn't invalidated by the network itself. This means establishing what we call the ICMP baseline.
Explain this process. We're talking about making sure the network can actually handle the size of the data the scanner is sending, right?
Precisely. Think of the maximum transmission unit, the MTU, as the maximum size of a truck your network allows on its roads. If your scanner sends a packet, what we call fat packet, that is bigger than that MTU, the network has to fragment it.
It breaks it into smaller pieces.
It does. And what happens when those fragmented pieces hit the AI scanner?
It probably doesn't like it.
It hates it. The scanner, which is almost always configured for speed, isn't designed to reassemble fragmented packets, so it just sees it as corrupted or invalid, drops it, and reports the target host is unreachable or unresponsive.
So the security team wastes hours, maybe days, hunting a ghost vulnerability when the only real problem was a packet that was too big for the network.
It happens all the time. A skilled human analyst, they'll establish their baseline first. They use ping with specific large buffer sizes, like ping Nevelo 1472. If they see fragmentation, they know immediately that the error is a network issue, not a target security fault.
That is a huge time saver. It just proves that humans check assumptions while AI just checks patterns.
Absolutely. And that strategic level of verification, it continues when we move to identifying the device itself. The second key verification technique is fingerprinting the stack.
Okay.
This is where the human edge really shines, using tools like Telnet or curl for what's called banner grabbing.
Banner grabbing. So essentially just asking the device, hey, who are you? But why would an AI scanner get this wrong?
An AI uses passive, non-invasive techniques. So it sees activity on port 80, it notices HTTP characteristics, and it confidently reports. Vulnerability found, this is an Apache web server, patch it.
Right, it sees the application layer.
It sees the application layer, but the human expert, they see the infrastructure layer.
That's the critical context shift.
It is. The human analyst runs the banner grab, looks at the server header, and instead of seeing Apache version, the header says clear as day, Cisco iOS.
Whoa. Wait. Running a web server on a router's management port is a completely different security scenario.
It changes everything. I mean, we connect this to the bigger picture. The entire remediation strategy is different. You are suddenly not patching an Apache vulnerability.
No, you're hardening a critical piece of networking gear, a router's management interface that was accidentally exposed.
You got it. And that is the difference between simple data recognition and true architectural understanding. The AI saw the pattern of HTTP traffic. The human recognized the underlying device and its role.
It proves the analyst is a detective, not just a scanner operator.
And that leads us to the final and I think most important step. Moving beyond just detection and verification to long-term defense. Finding a vulnerability is easy, relatively speaking. Engineering resilience, fixing it so that it stays fixed and resists future attacks. That's where the real solution lies.
So we shift from being reactive patchers to proactive hardeners. What does that strategic hardening look like, according to the sources?
It looks like following established standards, specifically the Cisco hardening standard. You don't just close a port. You architecturally deny access. This focus on resilience demands you use extended access control lists or extended ACLs.
What makes an extended ACL so much more powerful than just a standard port block?
A standard ACL might just block all traffic from an IP. It's a blunt instrument. An extended ACL is granular. It's strategic. It lets you restrict traffic based on two critical dimensions. Source IP, so who is sending the traffic and protocol, so what they're sending.
You're establishing a very precise rule of least privilege.
The most precise rule. So let's walk through the example they provided, just to make this crystal clear for you listening. The goal is to restrict management access, like SSH, to only the trusted admin subnet. So the human architect defines a permit rule for only that specific trusted traffic. The ACL rule looks like this. Access List 101 permit, TCP 192.168.10.0.255, any EQ22.
To break that down.
It's a very specific instruction. ACL 101, permit TCP traffic, but only if it's from the 192.168.0.0 network, and only if its destination port is 22, which is SSH.
And the power comes from what you do right after that, the famous implicit deny.
It's not just implicit. The human explicitly adds the catch-all deny any command at the end. This closes the door completely. If you didn't match that one single specific permit rule, you are denied. Access is surgically restricted.
So what's the resilience payoff of doing all that, of that architectural defense?
The payoff is architectural denial. This configuration denies an attacker, even one using sophisticated AI tools access, before they can even try to log in.
So it doesn't matter if they have the password.
It doesn't matter if they know the SSH password or have a zero-day exploit for the SSH service. If they aren't coming from that trusted admin subnet, the router's interface is simply inaccessible to them. The defense is built into the network structure, not just the application's login screen.
So what does this all mean for you, the security professional listening to this deep dive? It means the role is changing. It's shifting pretty dramatically. You're no longer just an operator of scanning tools.
That's right. The modern security role is evolving. You are now the verifier and the architect. You verify the AI's data points using those manual TTL checks, the banner grabbing to expose deception.
And then you architect the solution.
Then you architect the resilient solution using those specific targeted methods like extended ACLs to create a permanent defense.
The big takeaway here is that true security isn't achieved by just running an automated AI report. It's found in the meticulous verification of every packet, in the critical thinking about the architecture, knowing the difference between Apache and a Cisco router, and in the strategic hardening of that infrastructure.
That is the difference between a vulnerability report, which is just a list of problems, and a true security solution, which is a strategically hardened network designed to deny access before the attack can even begin. AI is a tool, but the human is the engineer. The human provides the resilience.
It's a powerful framework. It ensures we're focusing on solving the root problem, not just, patching the symptom.
And this raises a really important question, something for you to think about going forward. We've spent this time talking about how critical thinking and specific architectural knowledge are needed to verify things like TTL or the silent drop assumption. But the biggest challenge for the next generation will be anticipating the next wave of deception. What is the next filtered court trick attackers will develop, knowing the AI is trained to ignore it? And if we step back even further, think about how often AI is now being used in other high-stakes fields. Medical diagnostics, financial analysis.
What invisible TTL or silent drop assumptions might humans need to verify manually in those fields to stop a simple automated error from becoming a real crisis? The need for that critical architectural mind, it extends far beyond the server rack.